Hi, everyone. Welcome to today's speaker workshop. Our host, David Ramirez, is one of our advisors. He'll be holding today's workshop on large language model fundamentals and practical applications. A little bit about David is that he's the chief data scientist of Xponential.AI. He is also an engineering PhD candidate with a focus on applied machine learning. David has deep experience in the space and defense industry, where they have worked with image, video, radar, signal, and other obscure data types. David has delivered nearly 24 unique ML solutions to customers, worked as the technical lead of 75 plus engineers, and directly mentored over 200 technical professionals. Over the past few years, they have built and trained deep neural networks and large language models to fit specific business use cases. David became involved in artificial intelligence and machine learning research in 2014. These AI research advances are actively published to support renewable energy, remote sensing, autonomous vehicles, and military applications. David has co-authored nearly a dozen scientific papers while a student at Arizona State University, which is ranked as the most innovative public university in the United States. David's research interests focus on the computer vision, geospatial understanding, and multi-model large language vision models. David previously served in the United States Marine Corps, supporting military operations in nearly a dozen countries. David brings these leadership, mentoring, and team skills to everything that he does. David, thank you for your service, and I will turn it over to you.
Thank you very much, Rainey. And I'd like to thank everybody over at Kaggle, and everybody who's organizing this program, Rainey, Ray, and Kat, and everyone else. I'm excited to present here. Y'all trusted me enough to be the first presentation, so we're going to see how it goes, because we'll see if the demo gods are smelly today. My name is David Ramirez. Thank you for the introduction. We're going to be talking about large language models, the fundamentals of those, as well as some practical applications. And everybody here that's a fellow associated with the KaggleX program, y'all should be thinking about these practical applications, because that's the name of the game here, fine-tuning large language models. So the agenda today, I'm going to talk a little bit about my credentials, try to build some trust, so you might believe that I know what I'm talking about. I'm going to talk a little more about data science histories, where we're coming from. Today, generative AI is all the rage, but those techniques have been around for a while, and so I'm going to explain what techniques are older and which techniques are newer, and how they overlap. We're also going to talk about these fundamental building blocks of machine learning and AI, and I'm going to convince you by the end of this presentation that text, the words and digital text that you might read, that is numeric data, and representing that as numeric data is very important for large language models. I've got some live demos. We're going to click through those, see how they go, and finally, we're going to end with open discussion, somewhat open discussion, raised hand discussion related to applications for large language models. So if you would please hold your questions to the end. You can also drop questions in the chat, and I might see them. I've got it over on the other screen. If you see me glancing over this way, that's the chat, and I'm going to try to look at the camera for this one, but no promises there. So my credentials, as was introduced, I'm the chief data scientist of Xponential.AI, and a co-founder of that startup company. It's focused on commercial real estate, so automation and improvement and document understanding associated with leases and retail spaces and commercial real estate, and all the different businesses that occupy those sort of buildings. I've been doing data science since 2017, about 7 years professionally. I've delivered a bunch of different models, and I've gone through a bunch of different use cases, and I'll present those very briefly. Additionally, I'm a part-time student, sometimes a full-time student, and I've been pursuing graduate studies for 8 years, which is a long time to be in school as a graduate student. But it's because I've been juggling these two for so long that it's taken me a little bit longer. So I've been publishing research, and I'll talk a little bit about those topic areas. So here on the screen is not a comprehensive list, but it's many of the different projects that I've undertaken, been paid to undertake, either for my professional work or through research, academic research at the university. And so I'm not going to go through all of these lists, but the common themes here are computer vision and time series data. So I've worked a lot with imagery. I've worked a lot with other spatial data types. I've worked a lot with time series data types. And those two are coming together more now than ever before, with multimodal language and vision, large language vision models. And so I'm publishing those topics in research right now. And I'm also working with those sort of tools in the professional setting. Time series data is really related to this natural language processing stuff, and I'll show you more why. It's important to know where we're coming from a historical sense. The last decade has been packed full of AI advancements, but there's been a lot of older things that have come into play too. So data science, as we know today, I think comes from scientific beginnings, so to speak. Previously, before it was called data science, it might have been called statistics, informatics, analytics, quantitative research, signal processing is part of my background, predictive modeling, or perhaps even econometrics. And some of the founder of Kaggle had a PhD in econometrics. And even when I started my graduate studies, there was no such thing as a PhD in data science, but I think today maybe there is. But historically, access to the knowledge and techniques necessary to do this sort of work was hidden in academic dusty classrooms, and you had to pursue a PhD, 5 or 6 years of education to try to understand this material, and that was not very accessible to many people. And with the advances in the internet, open source software libraries, communities like Kaggle, the information has been released, and many more people are able to pursue and understand these techniques. So it's not just for PhDs anymore. But today in this presentation, I really want to make sure that everyone can walk away with an understanding of this information. So Rainey, I'm going to come back to you a little bit later, and I'm going to probe you with some questions and see if the information was at the right level for everyone's understanding. It was quoted here. Albert Einstein is often attributed to this quote: "If you can't explain it simply, then you don't understand it very well." And I want to prove to you that I understand what I'm talking about. And by doing that, I'm gonna try to simplify this into common concepts and simple speech. Okay, so data science trends of the last 15 years. This is, I think, everyone's been impacted by smartphones, so that's why I started the timeline. But perhaps it wasn't until this article, Data Science, the sexiest job of the 21st century, that people started using the term data scientist. Data science perhaps wasn't used that often. Kaggle was started a few years prior to this, but there wasn't that awareness yet in the public. And so this is a Google Trends search analysis. This doesn't necessarily represent how common these practices are, but they're more representative of how common the public and knowledge searches for this information is. So Google searches. It's not until maybe 2012 where there's this increase in this big data topic. People are collecting data from smartphones. Everybody's collecting data. Large companies, Google, big tech companies are collecting data. And that data is now a valuable resource, a valuable commodity. And people are learning that through advances in machine learning techniques, you can make use of that data. And so really machine learning starts to take off as a dominant force here. And data science is the practice, machine learning is the tool, and artificial intelligence is really the buzzword. But it's not until like the release of ChatGPT only last year, a year and a half ago, that people got this really huge renewed interest in artificial intelligence. And maybe that's what the term that people are using today. But as we all know, data science, machine learning, AI is all very related, as well as big data. So history of data science competitions. I just want to hit a few here. In the early 2000s, 2006, this Netflix prize was talked about in the academic sphere. And Netflix offered a lot of money if people could best their algorithms, if they could best them in recommending TV shows and movies for their customers to watch. And after a few years of academic research, trial and error, there was enough advancement in that field that Netflix awarded $1 million prize to the winners, the most prominent algorithm there. They were later sued by the users of Netflix for not having the right use agreements associated with the private data. And so that's an interesting tidbit. A few years later, this ImageNet challenge is presented in the CVPR conference, and this large-scale visual recognition challenge. And a few years of academic churn and development, and this AlexNet paper and neural network technique is the first to really break through with huge, tremendous results associated with image understanding using deep learning. And during that time, Kaggle is getting going, and in 2017, Google acquires Kaggle, and there's all these big prizes associated with data science competitions, and even the NeurIPS conference now has become a festival of just money flowing into these academic conferences, and that's really been a change. These academic competitions have been around for a while, but the money flowing into them, I think, is a new occurrence since 2017, perhaps, and even before that, with Kaggle being the first data science competition website, to my knowledge. Okay, so we're talking about generative AI now, and so what's new there? I want to present a really quick video. You might just have a flash of something really quickly. I think this is Van Gogh self-portrait painting, and you can see that it's slowly shifting into something very strange. It's like these little details are being pulled out. These textures are coming to the forefront. This is this so-called deep dreaming technique that was more popular 2015-ish, if I'm not mistaken. And you can see it's like sharpening out these little qualities, these textures of bird beaks and reptile scales and all these strange phenomena. And that's because a particular neural network that was used had an understanding of animals, and this image was sort of sharpened and imprinted with these textures that it had learned. So 2015 is deep dream technique. People were calling that generative AI, and I think today we're understanding generative AI to mean something else. But these first neural network building blocks have been around for almost a century. 1957, after World War II, people were thinking about ways to build neural networks and what the building blocks might be, but the computational resources weren't really there yet. It wasn't until much later that computers were powerful enough to do anything with neural networks. In the 80s, there was advancements in the backpropagation algorithm, but not until 2006, 2007, 2008, to that 2012 AlexNet paper, were there any substantial uses of accelerated computing for neural network computations. And so that's where things really started to take off. I mentioned that deep dreaming. That's sort of the origin of this term hallucinations. Weird like phenomena, anything that's sort of generated out of one of these techniques, you might have called a hallucination, and that was on purpose. If you could get the neural network to generate new, unique information, we would say that it would be potentially dreaming out generation. It would be dreaming out hallucinations, and that's what all generative AI is really doing. It's generating predictions. Sometimes they're factually correct, sometimes they're not. And today we say hallucinations are non-factually correct generations, but really a lot of generations you might say are just hallucinations. So 2017, these transformers come onto the scene and they become really prominent. And so let me ask you all, type in the chat, what's new today? Since 2017, what major advances have there been in natural language processing, large language models? What's been changed? Agentic flows, that's a great suggestion. Sahil, anybody else have a what's new in generative AI? What's new in language models? All right, I'm gonna keep moving on. What's new? Things are just bigger. Things are just huge. Um, it's there hasn't been any really big substantial advances in transformers in maybe 7 years. People are playing with small little tweaks and things, but GPT-4, the biggest, largest models, the most substantial high performance models, Gemini, um, Gemma that we're going to be using, these are, you can really just sort of compare and contrast them with the original transformers method, and they're really similar. It's only these small little tweaks that are pulling out a percentage points of improvement here and there. And so what's really making substantial improvements is the size of these models. And so 2017, the Attention is All You Need Transformers papers, the large version at 200 million parameters. In GPT-2, before it was ChatGPT, it was 1.5 billion, increased by a factor of, what is that, almost 10. And then GPT-3 and ChatGPT in this huge like waves through the industry, that's increasing by a factor of almost 100 to almost 200 billion parameters. And so had increased by a factor of 1,000 in just 3 years. Today, people are really pushing to make bigger models, but there has been some shift in trying to make more economical models that are cost efficient to run. And I think you see that in the size of the models that are coming into open source. The GPT-4, they've not released as an academic paper or really said the details of what those are, the OpenAI company, but there's an estimate of 1.76 trillion parameters. Here's another representation of that data. We've got like the red line at the top detailing what the largest models out there are at the time, and the time axis is on the x-axis on the bottom. You can see this upward trend of just growth and up and up and up. I've plotted the most common large language models here with word text. If you're interested to learn more, this is all Creative Commons information here hosted on this Our World in Data, the Oxford University, if I'm not mistaken. And you can see what other models their parameter count are, how many trainable parameters are in those models, and how does that really affect their performance? Well, I would say the larger the model, usually you get better performance. Maybe that's not the only thing involved, certainly not. Data plays a key role. How you train the model with what data and the quality of that data still plays a huge role, but the size is really important. Okay, so AI fundamentals. We're going to bring it back a little bit. We're going to talk about neural networks, the building blocks of these large language models. I'm going to relate some concepts from these huge large language models down to these itty bitty tiny neural networks, and they're very similar. So here in this simplified diagram, we've got a few images. Here is a cat, and down below is actually my personal dog. His name is Nassus. He's very cute. And if you might put an image into a neural network, you would see different data flowing through it. People call those activations. Perhaps you could think of it as water flowing through little sieve holes in the network, and you're trying to drip out this little information on the other side. I like to use a energy and electricity analogy because I'm electrical engineering background. You're activating these little nodes, these little circuits, and you're hoping that the correct little circuit at the end will be activated. A little light bulb will turn on because you pushed enough little electricity through the correct little circuits to illuminate the predictive model to say cat or to say dog. That's a simplified representation. So what's maybe a different way to represent that information? Well, people often show these interconnected nodes, these little numbers, and how they might be aggregated and pushed through a model. But you really can think of these as some giant math machine. Don't even worry about what's in there right now. Just know that it's some giant math machine. And we're going to take our input. Maybe it's a picture of a cat. We need to get some numbers out of that thing. So we need to create numeric qualities, what are called embeddings, but you might think of them as numeric qualities. And so we're going to populate that input with some numbers, numeric qualities. Then I think perhaps you'd agree with me that there's a way to take those numbers, multiply them together, add them together, multiply them by other factors, and eventually, after enough multiplies and adds together, you might be able to come away with these numbers on the other side. This 0.8, 0.1 numbers. There's some way to do that, right? Numbers in, multiply them together, big math machine, numbers come out. Perhaps not always the numbers that you'd like, but you can get some numbers coming out of this thing, right? And that's the core of neural networks. You push some numbers in, some numbers come out, and then you try to tweak the giant math machine to give you better numbers coming out, numbers that you would prefer it to give you. And that is true for this classifier, for cats and dogs, as well as other regression models. Really, what we'd perhaps like to see, instead of these arbitrary numbers, is some percentages. And this is what people are more familiar with. We can convert those arbitrary positive and negative values that come out of the model as the output. We can convert those into percentages. And now it makes a little bit more sense. The model's saying 67% confidence on that this image is a cat. And perhaps we can train it a little bit better, and we can increase that percentage. And we would say that that's higher accuracy. And that's often the technique that we're using here, is we're trying to push up these confidence scores, these percentages, these percent chances associated with this soft maximum technique. Okay, we're going to come back to that those were two different categories, cats and dogs, but these categories are really important for language models too. So text is numeric data, and I'm going to prove it to you. We're going to go on a quick field trip to the website here, and we're opening up some interaction here. So I'd like anybody to just, what would you like me to type here? We're going to do some language model stuff. The first thing I see in the chat, I'm going to type it in here, and then we'll maybe do a couple examples. So please type something into the chat, and I will bring it up in here. Something short, couple words. Banana head, love it. All right, here we go. Banana head, capital S. Okay, so we've got banana head coming out here, and these words are converted into numbers down here. Look at that. We're using the Google Gemma 7 billion parameter tokenizer. It's what it's called. We're turning words into tokens, which are really just numbers, number IDs. You can think of a token as a number ID. And so for this word banana with a capital B and no space at the front, the number is 75581. I bet we could, and the number for head here is 8487. Let's do another test. I'm going to put in banana again. Banana. And you'll see this is a slightly different number. What's up with that? Well, this one, if you look closely, the yellow at the top is including that white space right before this, the space. And so if we doubled that up and did another banana, you'll see that these two bananas, they are the same number. They're being represented by the same number. And it's this first one that doesn't have the space before it. But hey, if we put a space before it, now we've got the same number represented for all of these three. And that's what we're doing here. When we put in words, we get out numbers. And that's a big part of this thing is if you put in the wrong words, I kept misspelling banana. And it's going to actually split it up into different words, different tokens, because that's not a word in the dictionary of this model. In this vocabulary tree, this dictionary, all the words that it understands, the misspelled banana with an extra N in there actually needs to get split up into some partial subwords. And if that's trained into the model, you might get some weird results out of there. And so this is a concept that I'd like everybody to understand. If the words that you're trying to generate are not represented in the dictionary associated with the model, you might have a problem. And so make sure you understand that the obscure data points, maybe they're like, I don't know, code things or like silly emoji faces. I don't know. How are those going to be represented in the dictionary of the model? In this case, the little smiley face thing here does have a token associated with it. If we put a little nose on the thing, hey, that's got one too. So something interesting. I'll do one more example really quickly. Winter is coming. I like that one. We're gonna paste it in there. We've got some other numbers that come out. And if we double up on this thing, maybe we put a space. Even the space has its, or the new line character has its own token. And so think about that. How is your text data being converted into tokens? And how are you then gonna make sure that you've got the right tokens going into and coming out of your model? So now we're gonna talk about that. There are other tokenizers here that I would encourage you to explore associated with different models. But we're specifically using Gemma, and so I thought that was the best Gemma example I could pull up. Okay, so the ins and outs of large language models. We've been talking about it already. The inputs, numbers, the outputs, also numbers. This thing is a giant number crunching, giant math machine. And that's what you got to remember. It's not really doing anything particularly text-based. It's doing things with categories. Remember cat and dog, those two categories we have? Now we've got a whole dictionary of different categories, all these potential tokens that it could be. And in the case that I'm going to show here, it's almost got 300,000 words in its dictionary. And so that's a lot of different categories. That's much more than cat, dog, two categories, but it's nonetheless very similar. We've got a bunch of different categories, and we're going to try to predict one of those next words to be the correct category. And I'll explain more shortly. But the data processing steps here, if you're interested, we take in text, we convert it in those categories. We get those tokens, those ID numbers that I showed, and then we might convert those into numeric qualities, these embeddings. And that's what's going to go into the language model, perhaps. When the numbers come out of the language model, where they might be unscaled numbers, what do we do with these things? They're often called logics. Well, we probably need to scale them so we can understand them, and we're going to convert them into percentages on those softmax percentages that I showed, the percentage chance of this being the correct token of the next word to predict. With those percentages, we can train those to improve that through this backpropagation, training the neural network. And then eventually we go from those percentage chances to a real word a category, one of these tokens, and we can regenerate whatever text that we want to. We can generate new words coming out of the language model based on these categories. And that's the key concept here. So how do large language models do what they do? We've been talking about it here. We're going to say it again. Well, language models, most of them, they generate one word at a time, one token at a time. You can think of these all as next token predictors. And that's a way to simplify it. Sometimes we might aggregate multiple probabilities and don't even worry about it. The language model is going to generate one word at a time until it generates enough words to meet your query. And so one word at a time, sometimes that takes a little while. The next word might not always be perfect for what you want to get to, but that aggregation of one word at a time, it might steer the thing in a certain direction, which you're not necessarily intending. So something to keep in mind. Machine learning training, when we're going to train data into the large language model, we really might do so one token at a time. So when it generates a probability chance of what should be the next token, when it gets it right or when it gets it wrong, we're going to train that error back into the language model to try to get different words out of there, the words that we want. And that's going to be data dependent. It's going to, we need to bring the right data that it's going to have a good chance to get the right token, that next opportunity to get the right token correct. And so we bring in different loss functions. Oftentimes it's just a comparison between the word it chose and the word that you wanted it to pick. And that doesn't always line up. But you bring enough data, you train it long enough into the machine learning training process, you'll get some of the right words coming out of these things. Not always the right words. The generative pre-training technique is often used for generating next tokens. So when we don't care about what this thing does yet, we just can throw as much word sequences as we want at this thing. And it's going to learn a little bit about grammar, a little bit about word choice. We can use generative pre-training at scale. And that's often what we're going to get with these language models. They've been generatively pre-trained, but they haven't been fine-tuned for a particular task, like conversation, like a chatbot. They haven't been trained yet, perhaps, for instruction, question and answering, or others. And we're going to talk about all the varieties there in a second. So it's live demonstration time. Get hyped. I'm going to show some Google Cloud stuff. I'm going to show some Jupyter Notebook stuff, some Python, Hugging Face transformers. We're going to get into Gemma's, Google's Gemma model, using some PyTorch, some tokenization, some fun stuff. I'm not going to show error derivation and for backpropagation right now. I just don't think we have time. But I'll try to include that in the notebook that I deliver to y'all shortly. I think probably today or tomorrow. Okay, so what are we actually going to do here? We're going to download a pre-trained large language model. I'm going to use the base model, something that hasn't been fine-tuned for a particular task. And you're going to see that it's a next token predictor. Then we're going to run it in the forward pass to generate some text. We're going to inspect the inputs and the outputs, and I'm going to show you that those are numbers. And then we're going to recover text from those numbers. So let's do it. All right, let me close this thing. Let's go over here. Okay, here we go. I've got, I'm over on Google Cloud. Here we're in the Vertex AI shopping area. We're looking at the model garden. We got Gemma 2, fresh release, Gemma 2, not more than 2 months old, just released by Google. And we're going to use this, not necessarily through one of these Collab Enterprise notebooks or through a endpoint, but we're going to go through a Vertex AI workbench, which is essentially just a Jupyter Lab notebook. And so that's what I've got running over here. We're going to do a quick couple of pip installs to get Hugging Face transformers, to get Torch, and you know there's a PyTorch. There's not a PyTorch language. There's not a PyTorch large language models toolkit. It's actually Torch Audio because audio and time series data is very similar to language data, and tokens and these categories that we're talking about. It's sequential. And so we use the Torch audio package for sequential data. Okay, that's a just quick little aside. Let's run some stuff. I've got a kernel running here, and so I'm not going to do my imports again. But trust me that CUDA is available. Actually, we could just run these really quickly. I don't see why not. I'll show you that we're on a T4, one of the most inexpensive GPUs that you can rent on Google Cloud or anywhere. And so this is very accessible. You might need a little bit more for machine learning training, for large language model fine tuning, but for prediction, this is just fine. And this runs pretty quick. So I'm now going to load the Google Gemma model into memory on this machine that I've provisioned and that GPU. And so boom, into memory, real quick. Small model, only 2 billion parameters. 2 billion used to be a ton back in the day, but now 2 billion is a small model. Wow, times have changed. And so next, we're going to inspect this tokenizer. Google and Gemma has a certain tokenizer, and this one has 256,000 words in its dictionary. And I'm gonna show you that in a different way here in a second. Now let's generate some text. So I'm gonna take this tokenizer. We're gonna take some input text. We're gonna generate some of those categorical IDs that we were talking about before. I'm gonna print some information out. Then we're gonna send that to the model, and we're gonna ask it to generate some outputs. Then we're gonna inspect those outputs. We're gonna look at the size of those things, the numbers associated with those things, the softmax probabilities of these chances of the right categories being chosen. And then I'm going to prove to you that there are numbers going in and coming out of this thing. So let's do it. I'm just going to build that function real quick, and let's run it. So words go in is the prompt that I'm using for this model. And as a next token predictor, it's going to continue that sequence and generate more words. So I put in these categorical IDs. The 2 is the starting sequence indicator. And then we've got 3 different tokens associated with these 3 different words. Then I inspect the size of the output, the length of this output. And we've got those 256,000 potential words. There's still a potential. There's a potential that it could generate anything. But we want something good text. We want good text. So we hope that the probabilities on good words are high, and the probabilities on poor word choices are low. But who knows? So we're going to look at that output. Hey, look, a bunch of numbers came out of this thing, and they're like positive numbers, they're negative numbers, they're all over the place. And we really need to scale those to make sense of them. And so we're going to run it through this softmax function that we've been talking about to get some probabilities. We've got some very small probabilities. This is an exponential to the negative, very small number. We've got some slightly larger numbers here associated with this one right here. A bunch of numbers here coming out, probabilities, confidence scores associated with all the 256,000 tokens, potentials of next words they could choose. But the best one with the highest probability here, we've got 23% probability that we should pick this word as our next word. This word is 578. What token is 578, you might ask? Well, 578 is right here, 578. And that's one of the words that's generated in our sequence. So we go words go in, and 578, the token 578 is related to this and word. Look at that. And if we get the same words generated again, you would see this tokens repeated. So let's open it up on the chat. What would you guys like to put? What would everyone here like to see as an input here to this language model? What sort of word choice? Should we do winter is coming again? Winter is coming. And then I'll leave no space there. So we give it 3 different tokens, plus the starting sequence token. Those might be the same tokens that we did earlier. This is technically a different model. That was Gemma 1 and this is Gemma 2. So there's a potential they could be different. But I'd love to see somebody offer a suggestion in the chat. And then we get some random numbers coming out of this thing. We get small negative numbers. We get positive numbers. We scale them all to get those chances. These are small decimal probabilities. And then, hey, this is the best next token. And it says so with 24% confidence. Maybe that's much higher than the next one. And so we're going to pick this token as the next token. And hey, it's a comma this time. Interesting. And then comes the and. And wouldn't you know it, and is the 578 again. Okay, so I'm seeing some things in the chat. I like some unique words here. Godzilla. Godzilla takes Tokyo. I think that's supposed to be Tokyo. So let's do this. Let's run it. All right, so we've got 3 words generated. Godzilla takes Tokyo. I think Tokyo has a Y, but that's okay. We're going to go with that. We go through the same sequence. We generate these chances, these probabilities. And the next token it thinks is token 731. One of the potential words associated with this big dictionary. And that word is by. Godzilla takes Tokyo by storm in this 1998 film. The film is a remake. You'll see that this thing, it's not answering a question. It doesn't know how to yet. All it knows how to do is generate one word at a time. And so if we asked it a question, what type of model are you? And we run it, doesn't even know what to do. It says user 001. I'm a 5. Has no idea how to do question answering yet because it hasn't been fine-tuned for that task yet. Okay, I'll do one more example from the chat. We've got KaggleX is sample of Kaggle. Let's run it. So we've got 1, 2, 3, 4, 5. But we've got 1, 2, 3, 4, 5, 6, 7, 8 tokens coming out of this thing. Several of the words that we're using here are not represented in the dictionary. It's breaking those out into different subwords or subfraction of the words. And so think about that. It's going to have a harder time generating these words if they're not in the dictionary. That's the truth. Okay, so we could try to train that behavior into the model, but it would just be better if KaggleX was in the dictionary. And you can do that if you know how. You can add new words in the dictionary. You can specialize the dictionary for certain tasks. And I would encourage you all to explore that. The next sequence predictor, what it does here is it says Kaggle is a sample of Kaggle. It says data set, period. This is a sample of the Kaggle data set, period. It tries to continue the sequence. It even throws in a line break and really just doesn't know what to do. It's sort of repeating out the most likely next word. What I've done here is I've actually turned off sampling. So this is completely deterministic. Neural networks and language models, for the most part, are completely non-random. If I run this again, I will not get different results. I will get exactly the same results. So I'm going to run it again to prove it to you. The same. I could put in a different random seed. I could do all sorts of other random variations to this thing. It will be the same every time. It will not be different unless I turn on sampling. And so this is an important concept as well. If I turn on sampling, then from all of these softmax probabilities, these small percentages and stuff, every one of these words, every word in the dictionary, 256,000 of them, every one of them has a chance to be generated. And you will get much more variety in those words. You'll much more interesting conversation out of this chatbot. But it will be weird. Sometimes it'll be weird because it won't. You're doing random stuff right now when you do the sampling. So let's try it out. We have the same sequence going in, same tokens, but we have different tokens coming out now. KaggleX is a sample of Kaggle competition for data science and machine learning. This competition is on UCI machine learning dataset. Some interesting words coming out of there associated with data science. That's what you're getting. When you provide a small amount of context like this as the input, it's going to generate next words that associate with those words. If you say Kaggle, well, it knows Kaggle is about data science. And so wouldn't you know it, it generates some words associated with data science. So think about that. Even if this thing is untrained for a task, it's just a probability machine. It's just going to generate words associated with the input sequence. And that's what we're seeing. Okay, so I think I've driven home my point. I want to get to the final section of our presentation. So let's get back to it. All right, we did the notebook demo. Demonstration summary. We downloaded a pre-trained large language model, the Gemma one, Gemma 2. We ran it, the forward pass to generate some tokens. We inspected those tokens, those numbers, those categorical IDs, and that were generated on the output and in the input, and we recovered text from those numbers. And you should be thinking about this data processing steps when you pursue your project here as a KaggleX fellow. Okay, applications for language models. We're into our last 10 minutes of this presentation, and so I'm going to run through these really quickly, and then we're going to have some open conversation. And so if you'd like to get your hand up, we'll be calling on people with raised hands. So for fine-tuning large language models, fine-tuning machine learning in general requires two ingredients, the input and the output. You need the exact sequence of words as an input, and you need an exact sequence of words that you would like to be generated as your output. And so you need to bring that data, the exact sequence of words as an input, the exact sequence of words as an output. And those paired inputs and outputs, many of those will represent your data set. You'll need hundreds, perhaps thousands. So think about that when you're pursuing your project. Those data types, those inputs and outputs could be a variety of different things. They could be conversational chatbots. They could be tuned for instruction, question and answering, information retrieval, language translation, code generation, anything that has something to do with words and generating words and language, even coding languages. These are all great applications for language models. Language is in the name. So make sure that your particular application has something to do with generating language. Sometimes understanding language will work. Sometimes it will not. So make sure that you have enough understanding built into your data set to represent those input, what you would like it to recognize, and the output, what you would like it to generate. Okay, practical applications for large language models. Some examples. So here's some fun examples. If you were going to build a conversational chatbot, you need to bring this data, such as, can you please help me fix my computer? And you also need to bring the other half of that, the output, certainly what seems to be the issue. You need to bring both those pieces of data, and you need to bring them en masse. You need to bring a lot of these examples to fine-tune them into the language model. Additionally, you might use certain calls to tools, search functionalities, perhaps going out to the open internet and grabbing data, the most relevant and up-to-date information. Use of tools could generate some words for you, and you can include that as context, either in the prompt and the input, or perhaps after as a verbatim text associated with your output. So using tools, using search, using vector search with embeddings, there's lots of different things you could do there. Perhaps you're trying to build a question and answering bot. Well, you better bring the questions and the answers, because you need to bring both those data to train into the language model. You could even do more exotic languages. Up at the top, I've got Elvish. from The Lord of the Rings. And perhaps you could build a language model associated with translation to generate the Elvish language. Why not? It's a language. If you bring enough of that data into the equation, you can train that into the language model. You could do information retrieval, and in the most simple sense, you can do next word completion, just like we showed. If you give it a word, perhaps you want it to generate other words. For example, reptiles are my favorite type of animal. I could bring a bunch of these examples, perhaps personal information or something, and you could train that completion engine into your chatbot. Perhaps you could create a code completion engine, and we're seeing that more prevalent in search and IDEs, integrated development environments, coding stuff. So completion, that's another one, but that's the most simple. We showed that before, next token prediction. Okay, so now when we call on people, Rainey, I'm going to call on you really quickly. How am I doing so far? Is everything making sense?
Sounds really good, David. I love how you give the clear explanations and examples. Yeah, very exciting to get some feedback from our participants.
Yes, I see one hand raised. Kaya Clark, would you like to come off mute and participate with me here?
Yes. So I just had a question in terms of the models on Hugging Face. So I know like GPT-2 is listed as solely like a text generation model. I'm just wondering about like the GPT-3 and GPT-4. Are they combinations of different types of models that work together to be able to use like all the functionalities of GPT-4 that is used like regularly?
I think I understand your question. So the OpenAI company operates a lot of those products, right? GPT-4, GPT 3.5, Turbo, all these different services, right? A lot of those are not public information. We don't know exactly how they work, but they certainly are integrated with tools. And so you might have web search tools where the language model, perhaps it gets a token that pops up a categorical ID that says, go to the web and search this information or something. Perhaps there's a way that you can build in this search functionality to provide it as a prompt. So certainly they have tools integrated. They also have guardrails, and there might be multiple models, but there is certainly one very big language model that does that takes in numbers and generates numbers. And so I hope that answers your question. We can take this offline. I think that's more of a detailed question. What I like.
One more question. It's kind of, I guess, a more like straightforward question, but just between the differences of retraining a model versus fine tuning, like the Gemma model, and what would be the advantages or disadvantages and reasonings for doing retraining over fine tuning. I just wanted to know like what we should be doing specifically for our chatbot project.
Your question. I'm sorry to cut you off. To answer your question, they're very similar, almost identical. Think of them the same, and so there's no difference. If you're training or fine tuning, you're doing the same thing. So hopefully that answers your question. I'd like to do these things really quickly before we end the call. Would anybody like to participate on these examples with me? Does anyone have any ideas that they've been mulling over here with regards to their project, the KaggleX project? Anybody like to come off mute? If I don't get any participation, I'll be sad. Tear. All right, Olu, please come off mute.
Yes, I would like to participate.
Awesome. Do you have a project idea that you've been thinking about?
I have a lot.
Okay, give me an example. What would you like your chatbot to do?
I'm trying my chatbot to do predictive maintenance.
Predictive maintenance.
Yeah.
Okay. So you wanted to take in information about what's happening in the environment, and then perhaps make a determination about when is the right time to do predictive maintenance.
Yeah, more like taking input of machines bring out an output of how to mitigate wear and tear of the machines. Yeah.
Okay, how to mitigate? You want repair procedures, perhaps.
Yes. So the
Repair procedures. So perhaps this is an information retrieval task. You might have how-to manuals associated with your machines, and perhaps you could search through those how-to manuals when someone has a question. And I'm not sure if this is a question-answer type of situation, but perhaps somebody has a question such as, my machine is making funny noises. And maybe this is an engine in a car or something else. And what would you like it to generate? Maybe you want it to say, tell me more. Tell me more info about that noise. You need to bring this sort of question answer data, or maybe there's a different way to phrase this, where it says, what are the repair procedures for XYZ? And perhaps the response, the data that you need to bring to train into the model would be, this is the repair procedures, boom, boom, boom. And then maybe we go and call out to a search tool, and we go to our how-to document. We go to our frequently asked questions section. We pull that information verbatim, and we bring it into the language section, and we bring it into the generation. And perhaps that's how our chatbot functions. So there's many ways to run this different stuff. You could do it for instruction. You can demand something from the chatbot. You could do it for conversation, like a customer support, pretend to be a human speaker. You could do question and answer, but certainly you would want to pose a question. I didn't exactly do that here. Perhaps there's other tools integration, like we've been discussing too, including a web search or a document search. Okay, people are talking about token limits. Good questions, but probably too technical for this talk. And so I'd encourage you to speak with your mentors about limitations in language models, how to get around those, how to overcome problems, how to overcome challenges. That's what we're here to do. We're going to all hit a couple challenges associated with our projects. And so I think there's enough experience with language models associated with the KaggleX mentors and advisors and staff and everybody here that we can solve problems together if they arise. So I would encourage you to bring these problems into your discussion groups, and there will be discussions to offer suggestions, and perhaps you can get really closely with your advisor to solve them. So that is the end of the presentation here. Just a quick token joke. Here's an end of sequence token for the end of our text generation. So I hope you learned something new, and I'm gonna keep this exactly at 1 hour. So I can stick around for a little bit longer, but not too much longer. But Rainey, I think now is a great time if you'd like to end the recording.
Yes, no problem. Thank you, David. We appreciate your time today. Thank you guys for attending. Also, there